The ocean. It's a vast, dynamic world, covering over 70% of our planet's surface. It teems with life, from the smallest plankton to the largest whales. Its depths hold mysteries we are only just beginning to understand. We see its beauty, its power, its seemingly endless expanse. Yet beneath this majestic surface lies a constant, silent struggle. A struggle for survival, not just for living creatures, but for the very structures we build. For ships that traverse its waters, for platforms that extract its resources, for the vital infrastructure that supports our modern world. This immense body of water, so crucial for life, is also an incredibly harsh environment. At the heart of this struggle is a process called corrosion. It is a natural phenomenon, an electrochemical process. Simply put, it's the gradual destruction of materials by chemical reactions with their environment. Think of it like a slow, relentless rusting. But in the marine world, this process is supercharged. It eats away at metals, compromises structural integrity, and leads to costly failures. The ships we rely on, the bridges that connect our lands, the pipelines that carry essential fuels, all are vulnerable. This unseen battle costs economies billions, even trillions, globally each year. It's a fundamental challenge we must constantly address. What makes the marine environment so particularly aggressive? Several factors conspire together. Firstly, there's the high salinity. Seawater is rich in dissolved salts, especially sodium chloride. These salts make the water a much better conductor of electricity. This conductivity accelerates the electrochemical reactions that drive corrosion. Then there's the dissolved oxygen. Oxygen is vital for many forms of life, but it's also a key ingredient in most corrosion processes, affecting common metals like steel. The constant motion of waves and currents ensures a continuous supply of this oxygen to metal surfaces, fueling the destructive cycle. Furthermore, chloride ions, abundant in seawater, are particularly insidious. They are small and highly mobile. They can penetrate protective coatings and attack the metal beneath. They also play a role in breaking down passive films, which are naturally forming protective oxide layers on some metals. And it doesn't stop there. The marine environment is alive. Microorganisms, algae, barnacles, and mussels colonize submerged surfaces, a phenomenon known as biofouling. These organisms don't just add weight. Their metabolic processes can create localized corrosive conditions, accelerating material decay in what we call microbially influenced corrosion. Even pollutants in busy seaports can dramatically worsen the situation, turning coastal waters into an even more potent corrosive soup. Humans have sailed the seas for millennia, and for just as long, we've battled the ocean's desire to reclaim our creations. The fight against marine corrosion is not new. Our ancestors faced it with wooden ships, using pitch and tar. As we moved into the age of iron and steel, the challenge intensified. But so did our ingenuity. Over centuries, we developed several fundamental strategies. These traditional methods still form the bedrock of corrosion protection today. They are the tried and tested guardians, the first line of defense against the relentless assault of the sea. These methods, though perhaps not as dazzling as newer technologies, remain essential. One of the most common and intuitive approaches is the use of polymeric coatings. Think of it simply as painting. But this isn't just any paint. These are specially formulated polymers, long chains of molecules, designed to create a physical barrier. This barrier isolates the metal surface from the corrosive seawater. Epoxy resins, polyurethanes, and vinyl esters are common examples. They need to be tough, flexible, and able to adhere strongly to the metal. The aim is to form an impermeable shield, preventing water, oxygen, and those damaging chloride ions from reaching the vulnerable substrate. Their effectiveness depends heavily on proper surface preparation and application. Another stalwart in our protective arsenal is the use of metallic coatings. These involve applying a layer of a different metal onto the surface of the material we want to protect, usually steel. One widely used technique involves zinc or aluminium, or alloys of both. These metals are more reactive than steel. This means they will corrode preferentially, acting as a sacrificial anode. They give themselves up, so to speak, to protect the underlying steel structure. This is known as galvanizing when zinc is used. Thermal spraying is another method, where molten metal particles, often aluminium, are sprayed onto the surface to create a durable, protective layer, which has proven both effective and economical. Then there is cathodic protection, a clever electrochemical technique. It works by making the entire steel structure the cathode of an electrochemical cell. This effectively stops it from corroding. There are two main ways to achieve this. One is by using sacrificial anodes, as mentioned with metallic coatings. Large blocks of zinc, aluminum, or magnesium alloys are attached to the hull of a ship or a submerged platform. These anodes corrode instead of the steel. The other method is impressed current cathodic protection, ICCP. This uses an external power source to force a current through the water to the steel, preventing corrosion. Selecting the right anode material and consistently monitoring its performance are key challenges here. While traditional methods are vital, the quest for even better protection never ceases. In recent decades, a revolution has been brewing. A revolution at an almost unimaginably small scale, the nanoscale. Nanotechnology deals with materials and structures measured in nanometers, billionths of a meter. At this tiny level, materials can exhibit extraordinary new properties. Scientists and engineers are now harnessing these properties to create advanced coatings. These coatings promise significantly enhanced performance, offering a new generation of defense against the relentless marine environment. It's about making barriers smarter, stronger, and more resilient than ever before. One exciting development is the creation of nanostructured polymer coatings. For instance, incorporating tiny particles of titanium dioxide, or TiO2, into polymer matrices has shown remarkable results. These are not just simple mixtures. The nanoparticles are engineered to disperse evenly and interact with the polymer. This creates a far more tortuous path for corrosive agents like water and chloride ions. The result is a coating that is significantly more impermeable than its traditional counterparts. It's like building a much more complex labyrinth for the invaders to navigate. These nanostructured TiO2 polymer coatings offer superior protection by forming these incredibly dense and effective barriers. The world of two-dimensional materials has also opened up new frontiers. Graphene, a single layer of carbon atoms arranged in a honeycomb lattice, is one such wonder material. It's incredibly strong, lightweight, and an excellent barrier. MXenes, another family of two-dimensional materials, share similar promise. When these ultra-thin sheets are incorporated into coatings, even in tiny amounts, they can dramatically enhance barrier properties. Their vast surface area and minimal thickness create a layered, overlapping structure. This structure is exceptionally effective at blocking the passage of corrosive molecules. A 2024 review highlighted the significant role these two-dimensional materials are playing in marine corrosion protection, marking a clear step forward. Building on this, researchers are developing even more sophisticated functionalized nanocomposites. Imagine taking these nanoparticles and tailoring their surfaces for specific tasks. For example, a 2024 study detailed an advanced nanocomposite coating for aluminum alloys. This coating incorporated functionalized hafnium nitride, HFN, and graphitic carbon nitride, GCN, within polyurethane matrices. The results were impressive. Not only did it show enhanced corrosion resistance, crucial for marine superstructures, but it also offered improved flame retardancy and mechanical strength. This multifunctional approach is a key trend, aiming for coatings that do more than just prevent rust. They make the entire structure safer and more durable. Beyond enhancing existing coating types, scientists are also exploring entirely new classes of materials for protection. One of the most fascinating developments in recent materials science is the emergence of high-entropy alloys, or HEAs. Traditionally, alloys are based on one primary metal, with small amounts of other elements added to improve properties. Think of steel, which is mostly iron with a bit of carbon. HEAs, however, break this mold. They are composed of 5 or more principal elements, mixed in roughly equal or near-equal atomic proportions. This seemingly simple change in recipe leads to materials with remarkable and often unexpected characteristics. The concept of HEAs is intriguing. By mixing multiple elements in this way, the alloy structure becomes highly disordered at an atomic level, hence the high entropy. This disorder can lead to exceptional properties. Instead of forming complex, brittle intermetallic compounds, these alloys often form simpler crystal structures, like face-centered cubic or body-centered cubic. This structural simplicity, combined with the chemical complexity, can result in a unique combination of strength, ductility, and resistance to wear and corrosion. It's a new paradigm in alloy design, opening up a vast compositional space for exploration and discovery for materials scientists. When applied as coatings, HEAs demonstrate significant potential for marine applications. For instance, coatings made from alloys like alkographene have shown excellent resistance to wear, corrosion, and even tribocorrosion, which is corrosion accelerated by friction or wear. This makes them particularly suitable for components that face harsh mechanical and chemical stresses simultaneously. Imagine the moving parts of offshore drilling equipment or structures constantly battered by sediment-laden seawater. These are the kinds of extreme environments where HEA coatings could truly shine, offering a level of protection that conventional materials struggle to provide. The applications for HEA coatings in the marine sector are diverse and growing. They are being considered for submerged structures, propellers, pump components, and various parts of offshore platforms. The ability to withstand combined attacks from seawater corrosion and mechanical abrasion is a huge advantage. Research is ongoing, with a 2024 article discussing the progress and prospects of these anti-corrosion and wear-resistant HEA coatings, as highlighted by scholars like Fan and colleagues. As our understanding of these complex alloys deepens, and as manufacturing techniques for HEA coatings become more refined and cost-effective, we can expect to see them play an increasingly important role in safeguarding our marine assets. Section 5. Repelling the deep, the magic of superhydrophobic surfaces. Nature often provides the most elegant solutions to complex problems. Consider the lotus leaf. Water droplets roll off its surface effortlessly, carrying away dirt and debris. This remarkable self-cleaning property is due to its micro and nanostructured surface, which creates extreme water repellency, known as superhydrophobicity. Scientists are now learning to mimic these natural designs to create coatings that can actively repel water. These superhydrophobic coatings are not just about keeping surfaces dry, they offer a fascinating new approach to preventing corrosion and biofouling in the challenging marine environment. It's a kind of material magic, inspired by the natural world. How do these surfaces work their magic? It's all about surface texture and chemistry. Superhydrophobic surfaces typically have a rough texture at the micro or nanoscale, combined with a low surface energy material. This combination means that water droplets sit on top of the roughness, trapping a layer of air beneath them. Instead of spreading out and wetting the surface, the water forms almost perfectly spherical beads that can easily roll off, taking contaminants with them. This lotus effect dramatically reduces the contact time between water and the material, which is a fundamental step in preventing corrosion. The benefits for marine applications are significant. By repelling water so effectively, superhydrophobic coatings can prevent the formation of biofilms. Biofilms are slimy layers of microorganisms that are the first stage of biofouling. If water can't stick, it's much harder for these tiny organisms to gain a foothold. This means less biofouling, which translates to reduced drag on ship hulls, improved fuel efficiency, and lower maintenance costs. Furthermore, these coatings offer self-cleaning properties. Dirt and salt deposits, which can accelerate corrosion, are simply washed away by rolling water droplets. This is a huge advantage in the salty, often grimy, marine world. Innovation in this area is rapid. Researchers are constantly exploring new materials and fabrication methods to create more robust and durable superhydrophobic coatings. A study set for publication in 2025 by Tan and colleagues, for example, details a novel coag composite coating. This coating, fabricated via a one-step electrodeposition process, exhibited excellent superhydrophobic performance and significant corrosion resistance. A key challenge has been maintaining this water repellency after mechanical damage, like scratches or abrasions. Newer designs are now incorporating self-healing capabilities, or are inherently more robust, ensuring that the magic of water repellency lasts even in harsh, real-world conditions. And Section 6. Intelligent Protection. The rise of smart and self-healing coatings. Imagine a coating that doesn't just sit there passively, but actively responds to its environment. Imagine a coating that can sense damage and repair itself. This isn't science fiction, it's the cutting edge of material science. We are entering an era of smart materials and self-healing coatings. These innovations promise to revolutionize how we protect structures in dynamic and demanding environments like the ocean. They offer the potential for adaptive protection, enhanced durability, and a more sustainable approach to managing the ever-present threat of corrosion. These materials are, in a sense, becoming intelligent. Self-healing coatings are designed to autonomously repair minor damage, such as scratches or microcracks that would otherwise expose the underlying metal to corrosion. There are several approaches to achieving this. One common method involves embedding microcapsules filled with a healing agent, like a monomer or resin, into the coating matrix. When a crack forms, it ruptures these microcapsules, releasing the healing agent. This agent then fills the crack and polymerizes or hardens, effectively sealing the damage. Other intrinsic self-healing mechanisms rely on reversible chemical bonds within the coating material itself, allowing it to mend itself when damage occurs. Smart materials take this concept of responsiveness even further. These are materials designed to sense changes in their environment, such as pH, temperature, stress, or the presence of corrosive ions, and respond in a controlled, predefined way. For marine corrosion protection, this could mean a coating that releases corrosion inhibitors precisely when and where they are needed, or a coating that changes its properties to become more resistant under specific attack conditions. This adaptive capability is incredibly valuable in the constantly changing marine environment, where conditions can vary dramatically from one moment to the next, offering a more tailored and efficient defense. The development of these intelligent coatings is driven by the need for enhanced durability and sustainability. By repairing themselves, self-healing coatings can significantly extend the service life of protective systems, reducing the need for frequent maintenance and reapplications. This not only saves costs, but also lessens the environmental impact associated with coating removal and replacement. As highlighted by researchers such as Al-Jabouri and Shang in 2024, these innovations are key to providing adaptive protection under the dynamic conditions found at sea. The goal is to create protective systems that are not just barriers, but active participants in the defense against corrosion, thinking and healing their way to longer life. Section 7. Preparing the surface essential treatment techniques. The most advanced coating in the world will fail if it's not applied to a properly prepared surface. Think of it like painting a masterpiece. The canvas must be clean, smooth, and primed for the paint to adhere correctly and last for centuries. Similarly, in the world of marine corrosion protection, surface treatment techniques are absolutely vital. These processes prepare the metal substrate, enhancing the adhesion of protective coatings, improving their barrier properties, and increasing resistance to localized corrosion. They are the unsung heroes that ensure the success of the entire protective system, laying the crucial groundwork for long-term defense against the harsh marine elements. One widely used surface treatment, especially for steel structures, is aluminizing. This process involves applying a layer of aluminium or an aluminium alloy onto the steel surface. There are various methods to achieve this, including hot dipping, thermal spraying, and diffusion coating. The resulting aluminium layer provides excellent long-term corrosion protection in marine infrastructures. It acts as a barrier and also offers cathodic protection to the steel if the coating is breached. As Wang and colleagues discussed in 2018, aluminizing processes are a cornerstone for preparing steel surfaces destined for the demanding conditions found in marine environments, ensuring a robust foundation for subsequent protective layers. Another important technique is sol gel processing. This versatile chemical method is used to create thin ceramic-like coatings or to modify surfaces at a molecular level. The process involves the transition of a solution, the sol, into a gel-like network, which can then be applied as a coating and heat-treated to form a dense, adherent film. Sol gel coatings are particularly effective for developing organic-inorganic hybrid coatings. These hybrids combine the flexibility and barrier properties of organic polymers with the hardness and chemical resistance of ceramics. As Figuera noted in 2020, the sol gel synthesis process is key to creating a robust barrier layer, effectively sealing the metal from aggressive environments. These surface treatment techniques fundamentally alter the character of the metal's outermost layer. They don't just clean the surface, they can change its chemistry, its topography, and its energy. This ensures that when a protective coating is applied, it forms a much stronger bond. Good adhesion is critical because if a coating delaminates or peels away, the underlying metal is immediately exposed to the corrosive environment. Furthermore, these treatments can help to passivate the surface, making it less reactive, and can improve resistance to specific forms of attack like pitting corrosion or crevice corrosion. They are an indispensable step in the journey towards effective and durable marine corrosion protection. Section 8. Navigating the hurdles, challenges in modern protection. Despite the incredible progress we've made in understanding and combating marine corrosion, significant challenges remain. The ocean is a formidable adversary, and our efforts to protect marine assets are constantly being tested. Developing new coatings and treatments is only part of the battle. Implementing these solutions effectively, ensuring their long-term stability, and doing so in an environmentally responsible way present ongoing hurdles. The path to truly comprehensive and sustainable marine corrosion protection is complex, requiring continuous innovation and a clear understanding of the obstacles that lie ahead in this important field of materials science. One of the most significant challenges comes from environmental regulations. For many years, some of the most effective anti-fouling coatings, which prevent the buildup of marine organisms, contained harmful substances like tributyltin or TBT. While highly effective, TBT was found to be extremely toxic to marine life, leading to widespread bans. This has spurred intense research into more environmentally friendly alternatives. Current options often rely on copper biocides, but even these are under scrutiny in some regions. The drive is towards developing completely non-toxic solutions, such as foul-release coatings or innovative ecological inhibitors like sodium phosphate, which creates protective films on steel, as highlighted by Delmora and colleagues in their upcoming 2025 review. Achieving genuine long-term stability for protective systems, especially for steel materials in seawater immersion zones, remains a formidable task. Structures like offshore platforms, submerged pipelines, or the hulls of large vessels are constantly exposed to the full force of the marine environment. The combination of salinity, oxygen, water pressure, temperature fluctuations, and mechanical stresses creates an incredibly demanding scenario. As Hu and colleagues pointed out in a 2023 review, achieving decades of reliable protection often requires more than a single technology. It demands robust materials, meticulous application, and often a combination of different protective strategies working in synergy to withstand the relentless attack. Furthermore, the issue of microbially influenced corrosion, or MIC, presents a particularly complex challenge. As we've seen, marine organisms can directly influence corrosion processes. The interaction between protective coatings and these microbial communities is not always straightforward. Some microbes can degrade coating materials, while others can create corrosive microenvironments beneath an otherwise intact coating. Understanding and mitigating MIC requires a multidisciplinary approach, combining microbiology, electrochemistry, and materials science. Researchers are even exploring novel strategies like using beneficial marine bacteria to form protective biofilms that transition into mineralized films, offering a greener approach to corrosion control, as Liu and colleagues demonstrated in 2018. Section 9. A United Front, Integrating Old and New for Lasting Defense. The challenge of marine corrosion is immense, as vast and deep as the oceans themselves. We've explored the harsh realities of this environment, the relentless chemical and biological forces that seek to degrade the materials we place within it. We've journeyed from the time-honored methods of protection, the polymeric and metallic shields, to the cutting edge of nanotechnology, smart materials, and alloys born from entirely new design philosophies. Each step forward represents human ingenuity striving to overcome a fundamental natural process. The scale of this endeavor is significant, impacting global trade, energy production, and environmental stewardship. It has become abundantly clear that there is no single, perfect solution, no universal panacea to conquer marine corrosion entirely. The sheer diversity of marine environments, from cold Arctic waters to warm tropical seas, from shallow coastal zones to the crushing pressures of the deep ocean, means that different situations demand different approaches. The materials we seek to protect also vary widely, each with its own vulnerabilities. Therefore, the pursuit of a one-size-fits-all answer is likely to be futile. Instead, the future of effective marine corrosion protection lies in a more nuanced and integrated strategy. The most robust and sustainable solutions will inevitably come from a multifaceted approach. This means intelligently combining the reliability of traditional methods with the enhanced performance and novel capabilities of innovative technologies. We can envision systems where a durable conventional coating provides the primary barrier, augmented by a superhydrophobic topcoat for self-cleaning and anti-fouling, or perhaps a robust metallic coating working in tandem with a smart, self-healing layer that can respond to minor damages. Cathodic protection will continue to play its vital role, perhaps enhanced by more sophisticated monitoring and control systems informed by real-time sensor data. Looking ahead to 2025 and beyond, the field of marine corrosion protection is set for continued evolution. The global market for these technologies is projected for significant growth, reflecting the ongoing need. Research will continue to push boundaries, focusing on advanced alloy compositions, hybrid and node systems, and improved design considerations for longevity. The development of eco-friendly inhibitors, advanced surface treatments like aluminizing and sol gel processing, and even biofilm-based protection will be crucial. By fostering collaboration between material scientists, engineers, and marine biologists, and by embracing a strategy that unites the best of the old with the promise of the new, we can extend the operational life and reliability of our vital marine infrastructure for generations to come.